We'll start on page 731, number 1. That's just asking for expected cell count of a chi-squared goodness of fit test. That one should be pretty simple. It's asking basically if they're all the same. So there's 60 total. 60 divided by 3 is 20. So the expected cell count for number 1 is 20, which should be C. Okay? The second one, it says the resulting data is summarized in this table below, and it asks what's the degrees of freedom with this chi-squared test. Again, you have to recognize that that's a chi-squared goodness of fit test. And remember that your goodness of fit test has degrees of freedom of k minus 1, which is your number of categories minus 1. So for chi-squared goodness of fit test, degrees of freedom is k minus 1, which is k is the number of categories. Okay? Wow, that's kind of dancing around, isn't it? So that would just be 3 minus 1, which is 2, which is A. Okay? Number 3, it says the p-value associated with this test is 0.067. If the significance level of 0.05 is used, which of the following is an appropriate conclusion? So obviously we're going to fail to reject. If we fail to reject, no, it's not A. It's got to be B. There's not convincing evidence that there is a preference for one ice cream flavor or one flavor of ice cream over another. So the answer to number 3 is B. Four and 5 and 6, I think, were confusing for a lot of people as to pick out which test it was, because it didn't say test for association, or it didn't say, you know, difference. So here's the thing. This is actually trying to get you to understand what the conditions are for each of these. So the conditions for a test for homogeneity are that we have independent random samples. The conditions for a test for independence is we have a random sample. So we see the difference? So now that I said that, and we read this first one, number 4, each person a random sample of 300 female students, and each person a random sample of 300 male students. I think it's safe to say that those are independent random samples, isn't it? So this is a chi-squared test for homogeneity. So our appropriate null hypothesis would be B, the proportion of students who wear a seatbelt and the proportion who do not wear a seatbelt is the same for male and females. So that's why number 4 is B, because it's independent random samples. When I look at number 5, it says we sampled 100 people. We didn't sample 2 different groups, we sampled 100 people. We asked them if they use the on-campus recreational facilities, never, occasionally, or regularly, and then whether or not they lived on or off campus. So that wasn't 2 samples. We didn't sample the people that were on campus and then sample the people that were off campus. So that's 1 sample. So that means that's a test for independence, or a test for association. So that one is D. There is no association between where a student lives or use of recreational facilities. So that's why number 5 is D. Okay? Number 6, 50 female students at a large university were selected and 50 male students were selected. Again, we've done 2 independent groups. Okay? Each student in one of the 2 samples indicate how often they watch TV shows. And they have these viewing categories, and it says which of the following would be an appropriate null hypothesis for a chi-squared test based on this data. This again C, because it's a test for homogeneity. We have 2 independent samples. All right? Moving on to 7. 50 female students at a large university were selected at random, 50 male students. It's the same thing. So we have the following viewing categories: never, once or twice per week, or more than twice a week. So that's 3 columns. And then male and female, that's 2 rows. Now, it really doesn't matter if you flip that. So our degrees of freedom for those chi-squared tests are rows minus 1 times column minus 1. So that's, you know, there were 2 rows and 3 columns. So that's 2 minus 1, which is 1, times 3 minus 1, which is 2. So our degrees of freedom here is going to be 2, which is A. Okay? Number 8. Each person in a random sample of 200 males and in a random sample of 100 females were asked to indicate political affiliation by picking the following categories, and there's a whole bunch of categories there. Are the sample sizes large enough to support using the chi-squared test to determine if the proportion falling into each of the political affiliations is different from males to females? Okay? This, we don't know. There's not enough information here, and here's why. Remember how we calculate our expected cell counts. Each expected cell count has to be greater than 5. Well, our expected cell count for these tests is equal to row total times column total over the table total. Okay? So I don't know what the row total, what the column total, what the table total are. I just know that I've sampled a decent amount of people. So I have no way of knowing this. All right? So that answer to 8 is E. So that was kind of a tricky one. It's probably one that a lot of people miss if I give something like that on a test. Okay? All right, so they give us 100 car owners of compact cars, 100 full-size cars. They asked to indicate whether they were concerned, somewhat concerned, or very concerned about the increase in price of gas. So a chi-square test of homogeneity was done, and they got a p-value of 0.31. So we failed to reject there. So you really have to read the 2 answers and see which one. You never say fail to reject, there is convincing evidence. So it's always reject, there is convincing evidence. So that one was pretty simple. Number 9 has to be A. Number 10. Researchers classified each individual in a random sample of 100 community college students into one of 4 categories. So associate, bachelor's, master's, or PhD, and also by gender. If the assumptions for the chi-squared test are satisfied, the test statistic will have a chi-squared distribution in how many degrees of freedom? Okay, again, this is rows minus 1 times column minus 1. So it's 4 minus 1 times, what do we have, 2 minus 1? So we have, which is 3. Okay? So number 10 is B. Number 11, which of the following test procedures would be appropriate for determining if the data provides evidence that the proportions choosing each of the sections are not the same? Okay, we just have one column. We don't have multiple things. Now, goodness of fit they can put as a row or a column. That doesn't matter how they lay it out. Okay, but there's just one column. So it has to be a chi-squared goodness of fit test. There's not multiple things. There's not a rows and columns. So this is the chi-squared goodness of fit test, which I think was C. Yeah. 12. Which of the following conditions must be met in order for a chi-squared goodness of fit test to be appropriate? The population distribution does not have to be approximately normal, so 1 is false. N is greater than 30. That's a condition for a mean problem, so that's no good. Sample size is large enough so that all expected cell counts. 3 is the one. So 3 is the only condition there. Now we do have another condition, which is that we picked out a random or representative sample. So make sure that you understand that. Okay. 13, which of the following is the number of degrees of freedom for testing independence using bivariate categorical data that has been summarized in a 4 by 5, that just means 4 rows, 5 columns. Okay, so that's just 3 times 4, which is 12. So number 13 is B. I'm running out of space. 14. Let's hope I don't have to write too much. In a study of the foraging behavior of woodpeckers, males and females were observed landing on trees below the partial table of the summarized data. If landing location and gender are independent, then the expected number of males landing on the upper trunks of trees is in which of the following ranges? Oh man, this is going to actually make me do some work. I need more space. All right, so we could actually fill in this whole table, couldn't we? All right, so we have males and then we have upper trunk. So upper trunk, what's the total there for upper trunk? We've got what, 54? So we take that away from 246, so is that 192? Is that right? So the total, so if I'm, all right, let me do this. Why would we just know? I was just going to go ahead and calculate it. Yeah, I don't think we have to have a range. So my table total is 246, right? And then this is males, females. All that I'm really concerned with is row total times column total over table total. Well, this right here should be 192 because these all have to add up to 246, right? And then this right here is 139. So it says, what's the expected number of males landing on the upper trunk? So this is where I'm looking for my expected. So it's 192 times 139 over 246. 108.5, does that sound good enough? So that expected cell count is 108.5. So that's definitely plenty enough, but I guess that answer is D. Okay, so number 14. I don't know. I think it made more sense just to calculate it. I don't know why they just gave a range there. The p-value for a chi-squared goodness of fit test. Okay, so for any chi-squared test, I'm going to need more space for this. So for any chi-squared test, our distribution kind of looks like this, right? So this is your chi-squared distribution. Okay? The reason that there's such a bulk down here is this is what we're hypothesizing our value is, right at this edge here. We're saying, okay, this is where the data should be if these things are independent, if they're the same, or if we have a goodness of fit test. Okay? If the data fits perfectly, this is where it should fit. So let's think about this. Let's just real simply think, I roll my dice 600 times. Each one of those should come up 100 times. That's what I expect to happen, right? But I know that that's very unlikely. So I'm probably going to have a little bit of variation. So it might not be here. It might fall here, or it might fall here, somewhere in here. Okay? What happens, though, is what happens when it falls way outside the range? Okay, way out here. Our p-value is the likelihood of being at or more extreme than, I lost my train of thought, at or more extreme than where we saw our data values, okay? And that's where we get our chi-squared test statistic from. So it said the p-value for a chi-squared goodness fit test is the area to the right of the calculated value of chi-squared under the appropriate chi-squared curve. And it's always to the right. So here's my test statistic, right? And there's my p-value. If my data fits really well, I expect my p-value to be really big. I might have chi-squared way back here, right? If my data doesn't fit very well, I'm going to expect chi-squared to get way up, okay? Does that make sense? All right. Any questions on chapter 15? So let me